Our next speaker is Dr. Norman Jouppi. Norman Jouppi is a Google Fellow. He has been the technical lead for Google's tensor processing units since their inception in 2013. Norm has a long and distinguished record of innovation in high-performance processors, memory hierarchies, and storage systems. And he was the principal architect and lead designer of several microprocessors. Please welcome Dr. Norm Jouppi.
Hi, thanks. Thanks. Clicker, yes. Okay. So the title of my presentation is Immense Scale Machine Learning. And you may wonder why I chose the term immense. So there's a lot of extreme stuff going around, but I think of it immense as being relatively good, where extreme reminds me of, for example, jumping off a cliff in a wingsuit. So I went with immense. Okay, we're covering the big, the small, and the not right at all, because I think those are the three of the largest issues that we face with very large ML models. So first of all, I'm going to dive down to key principles, foundationals in several different areas to explain how we came to the design decisions that we did. So this chart here shows, the energy breakdown of typical instruction execution in a CPU. And you can see that if we have a 8-bit add, it's 0.03 picojoules, where the whole instruction is 70 picojoules. So that means that we're getting less than 1% efficiency if we're executing this 8-bit add on a CPU. Now, you can have things like AVX and try to group 8-bit adds together and do them in parallel, but the basic idea is it's still going to be swamped by all the other stuff going on in a CPU. And this was well known when we started the project. Mark Horowitz had been giving talks about this, had research in this area, professor at Stanford, and he gave the ISSCC 2014 keynote on this, and this diagram here is taken directly from that. So we decided in order to scale to the size that we needed to get rid of basically all that overhead in blue. And the solution that we came up with was to do matrix operations on a 256 by 256 systolic array. So that eliminates all kinds of complex control logic, and most importantly, as you'll see later, it reuses fetched memory and registered data 100 times. And if you remember from the last slide, that was a big part of the blue area. And we reduce the energy overhead per compute operation by 10x. And you might say, why not 100x? Well, there's a bunch of other things that have to happen, like reading data from memory and stuff like that. So that's why it gets watered down to 10x. This just goes into a little more detail about systolic arrays. Systolic arrays were first proposed in the 1970s. They were popularized for signal processing applications, but they were largely forgotten in mainstream computer architecture by the mid-1980s. The systolic array only contains multipliers, adders, and flops. It does, in our case, matrix multiplication. And so it's highly efficient. We've done an analysis and determined that we're within a factor of 2 of the theoretical maximum energy efficiency in our MXUs today. The wiring is done by abutment within the array, so things are just put next to each other. There's no wires between different blocks in the systolic array, so you've eliminated wiring, which can use up a lot of power. It avoids memory accesses because we use data that we've fetched 256 times. And there's no control logic. It's just one big pipeline. It goes ka-chunk, 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 and there's no kind of conditional branch or anything. So in late 2013, we started the TPU v1 project. And I named it because the ML workloads were basically tensor mathematics. So, and we had GPUs and CPUs, and so it made sense to have a TPU. It's an example of a domain-specific architecture, and John Hennessy and David Patterson have written about domain-specific architectures. It's architectures that are specialized for a specific domain of applications, not one particular application, but basically the entire space of a particular kind of application, in this case, machine learning. And I think we all know what tensors are. By doing this, we were able to provide 10x better perf TCO than contemporary alternatives that were around at the time. So this graph here from ISCA 2017 paper shows that we're from basically around 10x with high variation compared to CPUs and GPUs. Our first design was a simple chip because we had to design it in a matter of months. It went on a PCIe card, and it only accelerated inference because that's what we thought the bottleneck would be. However, when that chip was being fabbed, we realized training capacity and capability was the limiting factor to producing models. And when we talked to the people doing the training, they thought doing a training chip would be too complicated to build because a training chip would have to do all of inference and then about 2/3 more work for the training part for the back propagation, and that had some more complicated math and other things going on, gradient optimizers and stuff. So people thought building a training chip would be too complicated. So we like challenges, and we decided to build a training chip and a supercomputer around it. So the basic plan for TPU v2, the first chip that would support training, was don't invent anything more than necessary. So if you look at our TPU v1 paper, it had 77 co-authors. That includes the people who did the software, the compilers, even the people who did deployment in the data centers. And so that's quite a bit more than Seymour Cray's, I think roughly 20 people, including the janitor from the quote from IBM. But I mean, things have gotten more complicated since then. And we did it on a shorter time frame as well. Okay, so the other key thing that we wanted to do was co-design from the compiler down to chip design. Some of us have been around for a while, and we've seen that setting hard interfaces along the way really limits the ability of optimization. And so we had our own language, intermediate language, which is also available to program in XLA, which is Tensor basically optimized. And the XLA team was part of the original design team for TPU v2. So we wanted to start from a typical vector CPU architecture and add matrix operations. And I'll explain why that is in the next couple of slides. First, it's similar to how the Cray 1 extended previous scalar machines with vector operations in 1975. And you may notice that I put certain things in italics, like in 1975, and also the systolic arrays from the 1970s. One of the key principles in the design was that we wanted to look across the entire history of computer architecture and pick out, there's been so many things developed, pick and choose things that were most relevant to us and improve on them and adapt them for use in our system. So I think a lot of common systems today are more based on what the fads are in architecture versus kind of foundational principles like this. So one advantage of starting with a scalar machine with vector operations, which is, you might think of Intel with AVX512 in that category, is we start with an architecture model with a compiler and add stuff. One of the key things when developing a new machine is time to compiler. So time to tape out is one thing, time to compiler is where the real goal is. And so by starting with a well-known architecture, we could leverage well-known compiler techniques for matrices in HPC. And I'm glad that Professor Padua's talk was before mine. So we took a great advantage of all those optimizations that he listed on the slides. We used, for a scalar machine, an 8-operation VLIW architecture. And I've never been a big fan of VLIW machines, and I never expected to design one. But when you're doing 8-way issue and the compiler is under total control of the code, and we don't have any dynamic operations like cache misses because we have scratchpad memories and stuff like that. So everything is deterministic pretty much. VLIW makes the most sense. That's another key thing I think is being flexible to adopt things that, you know, are different than your previous way of thinking, because this is a different application space. And 8 instructions per cycle is a very beefy scalar core. It's nothing to sneeze at. So getting back to the ties into the Cray architecture, let me just put an aside here that getting this award is especially meaningful to me because I grew up in the upper Midwest where Seymour Cray was, and in college, for example, my best friend and I, we made our own Seymour Cray fan club with 2 members, so as an undergrad. So I've been a fan of his for a long time. So if you look at this diagram of the Cray 1 on the right, everything to the left of that 2-sided arrow looks like the previous 6600 and 7600 machines. So that basically enables scalar code to run pretty easily right off the bat. And then you can the compiler folks can spend their effort on using the vector machine, but you can get the machine up and running and debug a lot of it very quickly that way. So when it came time to add the vector, the vector hardware was added in a consistent manner. So we wanted to follow that kind of a model. Another key thing that we had, there's been a lot of research on shared memory multiprocessors in the late 80s and early 90s, is we connect the TPU chips with a shared memory architecture that's distributed and uses a high bandwidth torus. The torus is very high bandwidth. It's similar to the Cray T3D's 3D torus, but it's much simpler. And it leverages, the torus is a natural fit for tensor math because, you know, you can map dimensions of the matrices to the dimensions of the torus. The ICI is 50x faster and 10x cheaper than Ethernet. And how did we do that? Well, first, it's really like a memory interconnect on like a 2-socket server board. There's no layers of protocol stacks. Many connections are PCB printed circuit board traces or cheap copper cables between boards. So ICI is the second key TPU feature after the systolic arrays. When we did some scalability studies using the ICI, we got these results. The 8 benchmarks on the side are key applications served to billions of daily users at Google, so they're not toy benchmarks. We got 99% scaling efficiency on 75% of the workloads to 3,000 TPU v4 chips. So that's pretty good. The two applications that didn't scale so well, the DLRMs, make extensive use of all-to-all communication, and so our bisection bandwidth in the first couple of machines wasn't high enough to support the scaling of those past 1,000 nodes. Another key feature of the TPU systems was that training was currently being done on CPUs and GPUs using FP32. Jeff Dean and the research group there were using this. And Google software stored the FP32 values, the 16 high-order bits of those, and to save storage. And what they did for the conversion to 16 bits, brace yourself here, was performed by simple truncation. So I know any numerical analysts here, you comfort them. This preserved the dynamic range while reducing precision. And they called this data type bfloat16 in the software. And it worked. So you can't really complain about the truncation that much. The existing 16-bit formats like FP16, which were developed for graphics, didn't have enough dynamic range. And we realized, looking at the software, that we could supply bfloat16 inputs to multipliers, keep all the product bits, you know, because n by n multiply of mantisses gives you 2n bits, so we kept all the bits. We didn't do any rounding or throw anything away. That becomes FP24, and then perform FP32 accumulations and get identical results as the current software was getting. This had some economic advantages in that it made the multiplier smaller, and we decided to round to nearest even because we couldn't face ourselves if we didn't do that in the morning. But most importantly, it maintained software compatibility with CPUs and GPUs. And again, this is going back to the development story of being compatible with things to get things up and running fast, and then adding additional stuff on top. So models that trained on CPUs, GPUs, and TPUs could all get the same exact results. Now this is a bit of a fib here, because we all know that floating point addition isn't associative, and sometimes different compilers would arrange the arithmetic in different orders, and we'd get different results, but it's only on the small, lower bits. So hence, BF16 was the third key TPU feature to get it up and running fast. So our first training-oriented system was TPU v2. It had 256 chips connected in a 2D torus. The ICI only ran at 2.56 terabits per chip. So compare that with like 100 gig Ethernet, for example. It was air-cooled to lower power consumption and improve time to market. And people don't really like it when I say this, but one of the key reasons for TPU v2 was to provide a working software development vehicle for future systems, because it can take a year to develop a well-tuned compiler, or more. Yeah, you can do that forever, but most of the gains come in the first year. So while we were bringing up the compiler on v2, we did a quick spin where we optimized the chip design layout. Instead of a sea of gates, we turned it into a data path, which we didn't have time to do in v2. We have a larger scale, 4x the chips and 2x the racks. We adopted water cooling so we could run the chip faster. Optical cables were available to do wraparound links. And HBMs at the time had twice the capacity. So that gave us overall 10x the TPU v2 performance. Okay. The next major step that we did was in TPU v4p. That has 64 racks of water-cooled compute, and there's 8 shown in the photo. And so those 64 racks together provide an exaFLOP of compute. And we have many such superpods connected via data center networking into bigger clusters. That's no secret. So what's a superpod? Well, one of the issues is reliability, availability, and serviceability, and I'll be talking more about that later. But we also get jobs of different sizes. Someone may want an 8 by 8 by 4 arrangement of TPU chips to match their application. Others might want a 16 by 8 by 16. We actually have some models that prefer 32 by 1 by 1, believe it or not, and they form, a pipeline along the 32 dimension of layers that are 4 by 4 TPUs. So that's one rack. So you can do that if you have optical circuit switching, which I'll talk about in a second. And also, you can see these skull and crossbones on the diagram. And if a rack goes down for some reason, we treat a rack as a unit. So it has 64 TPU chips in it and some servers and networking. So data center networking connections. So if anything goes down in the rack, we can just stop using it until it's repaired, and then it can be used in production again. So we connect the racks with optical circuit switches, and each rack is a 4x4x4 torus. Sorry, it is a 4x4x4 mesh, and then we can make it into a torus if we do wraparound connections with the optical circuit switches, or we can combine them into larger size slices, is what we call them. And we use different OCSs to connect different indices of the faces to corresponding indices of other blocks. Okay, and we have a video here about the V5 generation, where we increased it from 4,096 chips connected via OCS to close to 9,000, and this version is over 4 exaFLOPs. So it's a short video. Please take it away. Okay, great, thanks. Just pointing out, Sundar at the most recent Google I/O showed a picture of one of our coolant distribution units, which appeared in the video on the side, and noted that we have around 1 gigawatt of deployed liquid-cooled capacity. And he also mentioned that the TPUs are the only thing that we have that are liquid-cooled, so that gives you an idea of our TPU capacity. I realize I'm running out of time here, so I'll try to go quickly over the next slide. So I think we're familiar with the end of Dennard scaling. What that means is that the power density of chips is going to go up every generation from now till the end of the lithographic scaling. And so power and cooling is going to be a lot more important. So I notice on the floor at the exhibition this year, there's a lot of cooling companies as well as electric supply companies like Schneider. And John Hennessy in a plenary talk showed this slide, and a picture really hits it home. As you're scaling the technology down in the kind of the actual power per square millimeter goes up like very dramatically, exponentially. One of the things that consumes a lot of power is SRAM. If you look at this chart here, you can see that accessing a 1 megabyte SRAM is 100 picojoules, but doing a floating point multiplier that's 16 bits is only 1 picojoule. So that's why we're trying to reuse data 100 times. And it's even worse since Mark's 2014 keynote. Computation has gotten 3x denser and lower power, but SRAM is about the same. Moreover, the needs for memory capacity have been going up dramatically. There's the trillion parameter model that was mentioned earlier. People are talking about numbers much larger than that. So this is a plot of model size over time. And it's a logarithmic scale as well. So it's an exponential curve on a logarithmic scale. Pretty amazing. And reduced precision formats are important to further reduce energy costs and also the memory footprint. But of course, we can't get an order of magnitude smaller than bfloat16, which is only 16 bits. But using smaller data types will require automation to be effective. And one of the reasons for that at Google is we have to preserve accuracy compared to the larger formats, because one mistake in a billion can make the news. Okay, and then the not right at all. So RAS, it's the feature that everyone likes to complain about, but not too many people are working on it, it seems. In the previous generations, it received a lot of attention from finance and supercomputing, which is great. Now it's a significant issue in ML training. And we don't need real-time reliability like the banking industry or stock exchanges like the tandem style. But because recovery from checkpoints is okay, but errors must be detected and overhead from restart can be burdensome if it happens too often. So that brings us around to silent data corruption. I don't know about you, but I'm a fan of the space program, and there's Gene Kranz, head of mission control, wrote, "Failure is not an option." And for us, compared to silent data corruption, failure is a good option, because then you know it happened. But we need to detect them. And I think further research is needed in this area, like algorithm-based fault tolerance. There was some early work done at the University of Illinois in the late 70s, early 80s on this, but it kind of waned after that. So just to conclude, I think research in AI is advancing at a tremendous pace, and I believe much good will result. One of the things I'm most excited about is advances in science, like Bill Tang's presentation. And I think that ML may eventually become the fourth leg of science after experiment theory and simulation. Also provides knowledge tools to everyday people, such as language-based, image-based language translation. When I went on vacation to Japan with my family, you could just hold up your phone and then read things in Japanese. There's a lot of things, and we're just getting started. But we're limited by the amount of compute to run these tools that we need. So there's plenty of room for additional research. Besides exascale, we're looking at YADA and RANA scale, which is pretty amazing. Okay. Thanks, everyone.
Thank you very much, Dr. Jouppi, for that insightful talk. We'd like to take a few questions from the audience for Dr. Jouppi. Maybe one question.
Yeah.
Okay, I see one over here. Quickly.
Yeah, so my name is Brad Beckman from AMD. So very interesting talk. You mentioned the reliability challenge at the end. And also earlier you mentioned the fact that your BF16, basically in general also these smaller data types have round-off error issues, right? And so doing something like algorithmic based check, error corrections, have the challenge of dealing with the round-off error. Like if you're computing a checksum, simultaneous or with your matrix multiply. So I guess with that all in mind, the question is are folks in the ML design space willing to move to different formats that are maybe easier to do algorithmic-based correction for, rather than the low precision floating point?
Yeah, so the BEF16 works fine even if you truncate. So it's not like we're short of precision and have to do something special to recover it there. In fact, FP8 currently looks promising, and we've seen results even with int4. Now, the precision you use does vary depending on what you're doing. If you're doing second-order optimizer calculations, because those basically effectively have the precision when you do those calculations, you have to start out with something bigger like FP32. But it's, machine learning doesn't need a lot of precision.
Okay, thanks.
All right, let's thank Dr. Jouppi again.
Well, that brings us to the end of this session. We would like to thank you all for attending and listening to our speakers. Have a good day.